All right, so hi guys. This is Ms. Baker, and unfortunately for Tuesday, the 26th of January, I'm going to be out for pretty much most of the day. There's PSAT testing, and they pulled me to do testing. So I'm going to leave the lesson in the folder for you guys to complete asynchronously. There are some videos in that folder. I'm going to do my very best to pull the YouTube videos to make them into videos on Microsoft Stream so that you guys can view them. But I am also going to quickly go through the types of reactions. I think Tyler DeWitt does an absolutely amazing job of going through the 5 big types of schemes of reactions. That's the first video in the folder called Types of Chemical Reactions. That's the Tyler DeWitt video. I think he does an awesome job, but I'll go through it very, very quickly. The part that I really want to emphasize is the information that he doesn't give you, which are about the 3 different reactions that exist by nature. And those are precipitation reactions, acid-base reactions, and redox reactions. All right, I'm going to slide over to my document camera. So see ya. And now I'm over here. So really quickly, the big concept here was for us to be able to identify types of reactions, to look at a reaction and know what type of reaction it is that we're looking at. And we've already seen these names before. I told you guys that we would talk more about it next class, and next class is finally here. So our 5 big types by scheme are synthesis, decomposition, single displacement, double displacement, and combustion. When it comes to the different types of reactions, for synthesis reactions, we've seen these before. Basically, this is when I take 2 different or multiple different compounds or elements, and I bring them together to make some larger compound. So I represent that with A plus B gives us AB. All right, and we've already seen a couple of examples of that. Note that none of these reactions are balanced, right? All of the reactions that follow are unbalanced. So these are not balanced reactions, okay? So that's synthesis. We take 2 smaller things and we put them together to make one bigger thing. With our decomposition reactions, it's the exact opposite. We have one larger compound that we're going to break down into smaller component parts, whether these are smaller compounds or these are the elements that make up this larger compound AB. Either way, a decomposition reaction, we're going to take something big and break it down into 2 smaller parts or multiple smaller parts. And here we have a couple of examples of that. There are combustion reactions. These are the reactions I said in the last video that I hate balancing because they're so tedious. But combustion reactions occur anytime we have some hydrocarbon. So that's a compound that contains carbon and hydrogen. Sometimes they'll also contain oxygen. So here we represent that with the CXHY. And the reason we represent it that way is just because we don't know what those numbers are. So we just name them with variables. Just in case that compound does contain oxygen, right? Because sometimes they do. We have here O and then Z, sub Z in parentheses. So maybe this compound contains oxygen, maybe it doesn't. So I have it in parentheses here. This is a Z, a letter Z as the subscript on that oxygen, and that's to represent whatever number of oxygens we have as part of that compound. You can see on the other side of the compound, our products that will yield are carbon dioxide and water. So this is a real easy giveaway. Anytime you see some hydrocarbon reacting with oxygen to give carbon dioxide and water, you're definitely looking at a combustion reaction. And here we have a few examples. All right, and we also have some balanced examples in the previous lesson. Single replacement reactions. These are reactions where we start out with one element by itself, and by the end of the reaction, that element has replaced some other element in the original compound, kicking it out. So we represent that here with this A plus BC yields AB plus C. You can see that the A kicked out the C and replaced it in the compound, and leaving C out by himself. All right, we've got a couple of examples of this. I also loved how Tyler DeWitt used the little stick figure example in the video, so I went ahead and copied that into my notes. All right, you can see the green guy and the orange guy and the pink guy by himself. And we can see on the other side of the reaction, the green guy is now by himself and pink has kicked him out and replaced him. All right, kind of a sad fate for the green guy, all by himself, lost his partner. All right, the next reaction we have down here is double replacement. This is when the positive and negative ions in two compounds are going to switch places. Here we represent that with this scheme AB plus CD yields AD plus BC. So you can kind of see that there's a switching of partners happening here. And I love, again, how he represented that with the little stick figures. So I've color-coded that in the notes to also show you the trading of places of the cation and of the positively charged ions. So the Ba and the sodium, so the barium and the sodium. On this side of the equation, you can see how they've switched anions. So barium started out with chlorine, now sodium ends with chlorine. Sodium started with sulfate, now barium ends with sulfate. And I've got another example down here. That goes over the stuff that Tyler DeWitt talked about. I also want you guys to be familiar with a different way for us to classify reactions. We can also classify reactions as being acid-base reactions, precipitation reactions, or oxidation reduction reactions. Sometimes we call it redox. Note that a reaction can be one of the 5 that we've already seen, and also one of these 3. In fact, oftentimes that happens a lot. For example, under acid-base reactions, these are anytime we have an acid and a base that are going to react to form a salt and water. Here's a great example here of hydrochloric acid mixing with sodium hydroxide to give sodium chloride, salt. This is table salt. And there are other salts, right? Any salt is just going to be a halogen and a metal ion. Plus water, right? Water is one of those byproducts. You don't have to be able to know every acid-base reaction, but there are some things that you can look for to be able to point it out, right? Anytime you see an acid, right, those are our compounds that have an H at the beginning, a hydrogen at the beginning of the compound. And I missed a parenthesis here. And a base is typically going to contain the hydroxide ion, this OH minus, but it also can possibly contain the ammonium ion, NH4 plus. All right, so either one, but typically we're going to see this OH for our acid-base reactions. Not always, sometimes it's ammonium, but most of the time it's hydroxide. All right, when you see those as reactants, and you can confirm it if you see water as a product. All right, this is what you should look for when identifying an acid-base reaction. Is that acid, the H in front of its compound, and a base, typically containing hydroxide or ammonium. For precipitation reactions, this is anytime we have 2 solutions of ionic compounds that react and a precipitate, right, a solid that falls out of solution is formed as a product. All right, you might have noticed that I've been using these little parentheses with a little couple of letters or sometimes just one letter inside of those parentheses next to a compound, next to the formula for a compound. And these little letters and parentheses are simply indicating the state of matter. So if you see an S as the state of matter, right, you're looking at a solid. If you see an L as the state of matter, then we're talking about a liquid. I don't see an example here, but if you look at an example that has a G, right, that G tells us that the state of matter of this compound or this element or whatever it might be is a gas. The only one that might be unfamiliar to you is AQ. AQ just means, it stands for aqueous. Aqueous just means that, so I'll put this aqueous. And aqueous just means that it's in solution. So the compound itself is not liquid, it's just dissolved into a liquid. That's what aqueous means. All right. So for our precipitation reactions, I've got a great example right here with this barium chloride reacting with sodium sulfate to give barium sulfate, which is going to fall out of solution. It's insoluble, so it falls out of solution. And we can see that it is a solid on the product side, as well as NaCl, which is still going to be dissolved in solution. That's why we've written aqueous here. The big look for our precipitation reactions is going to be 2 ionic compounds with an AQ in the reactants. So here with the barium chloride and sodium sulfate, they're both aqueous and they're both reactants and they're ionic compounds. And in the product, we should be looking for 1 compound that has an S as its state of matter, a solid That means that it's fallen out of solution. It's no longer soluble in the aqueous solution in which the reaction is taking place. The last one you guys should be able to look at and identify are oxidation reduction reactions. A lot of times we shorten that down to redox. That's coming from the re part here and the ox part here, of the red part. So red and ox. So redox. All right. Redox reactions can get pretty complicated. I simplified it as much as I could here, but there's so much more for us to talk about. But I just need you guys to be able to recognize if it is a redox reaction. Pretty much all other reactions that aren't acid-base or precipitation reactions are going to be redox reactions. So what's happening here is that there's a transfer of electrons between the two reactants taking place. One of the reactants or one of the elements we could call an electron acceptor, which is an oxidizing agent or the element or compound that is being reduced. And then the other reactant is an electron donator. It's the reducing agent or the species that's being oxidized. That's a lot of information. Like I said, this is as concise as I could make it. But the big look-fors here, we've got a couple of examples and we've got our look-fors. The way I like to look for a redox reaction is if you can see a free element on one side of the reaction that is in a compound on the other side of the reaction, you're most likely looking at a redox reaction. And I've got a couple of examples here. When I say a free element, I mean that that element is not in a compound. It's an element by itself. For example, in the first example, this Na, this sodium hydride yields sodium and hydrogen. Here, the sodium is a free element, and on the other side of the reaction, we can see that it's in a compound. This is a redox reaction. Here in the second example, this this iron reacting with oxygen to give us iron, I believe this is iron 3 oxide. And for this reaction here, we can see that the iron is a free element on the reactant side, but we can see that it's in a compound on the other side of the reaction. This is also a redox reaction. The last example I have here is this copper sulfate reacting with solid zinc to give copper, a solid copper, and also zinc sulfate, right, which is aqueous. Here we've got zinc on one side of the equation, that's a free element, and on the other side of the equation, it's in a compound. Actually, the same thing exists for copper. Copper is a free element on one side of the reaction, and on the other side of the reaction, it's in a compound. You'll notice that I've highlighted in blue that these reactions down here can also be classified as some of the 5 big reactions we saw on the previous page, right? So this sodium hydride reaction is also a decomposition reaction. This iron 3 oxide reaction is also a synthesis reaction because we have 2 smaller components being brought together to make one larger component. This is a decomposition reaction because we have one large compound being broken down into smaller parts. For this copper sulfate and zinc reaction, this is a single replacement. And we can see that copper and zinc are switching places in the reaction. So first we start with copper sulfate and zinc. Now copper switch places with zinc so that we have zinc sulfate and solid copper. All right. I hope that this helps. Please do message me on Remind if you have any questions. It's the easiest way to get in contact with me, and I see them right away. Or you can also send me an email or a Schoology message. All right, I'll see you guys later. Bye. And stop recording.